Hello, welcome to KGOU's How Curious, the series dedicated to stories from around Oklahoma. I'm Rachel Hopkin. Oklahoma geophysicist Jan Dodson emailed me a few months back to tell me about an event that would shortly mark a seminal but little-known part of our state's history, how Oklahoma became the birthplace of reflection seismology. The event was called the Seismic Reflection Centennial. It took place over 3 days in April, and it included a range of presentations plus a one-day field trip. I'll be the first to admit that I'm not that great on science, but Jan's brief missive made it clear that the seismic reflection work carried out here in 1921 had been momentous. And by the way, COVID pushed the celebrations by 2 years. So what is seismic reflection? It's a methodology that uses ground vibrations to explore what lies beneath the Earth's crust. Since its invention, it has generated untold economic wealth through its ability to locate natural resources such as oil and gas. In addition, its principles have been deployed for many other important purposes. As we set off on the field trip, I asked Jan Dodson to outline the circumstances which had precipitated this world-changing innovation.
Oklahoma has been a huge oil and natural gas producer historically. The Native Americans found oil and gas seeps like around the Arbuckle and Wichita Mountains in Oklahoma. And at the time they weren't using it for gasoline, but they were using it for medicine and all kinds of things like that. And then internal combustion engine was developed, and there was a demand for gasoline, which is a refined product from oil and gas. So because there were seeps in Oklahoma, people began drilling.
The early methods used to locate those resources were pretty rudimentary.
They started drilling on what we call a surface high. It's probably not even a hill. It's maybe just 10 feet.
Why would that 10-foot high indicate oil or gas below?
When rocks are originally buried, there is organic matter buried with them. And as more rocks accumulate on top, it gets compressed and hot. And so chemical changes happen, and the organic matter begins to convert into oil and gas, into hydrocarbons. Hydrocarbons are lighter than the rocks, and they begin percolating upwards.
Think of cream rising to the top of milk, but you can usually easily scoop the cream off with a spoon, whereas oil and gas are often hidden below the Earth's surface. In order to find significant stores of them, you need to find places where reservoirs have formed in traps between two different layers of rock. These rock traps tend to follow certain formations, including the shape of a dome.
If the geology is a certain kind of geology, that dome will be expressed slightly at the surface of the Earth. Surveyors went out with their very basic survey equipment 100 years ago and surveyed what we call a topographic high. And they drilled there, and sometimes they found oil and sometimes they didn't.
Since topographic highs can be caused by a host of other activity, including erosion, the success rate was very hit and miss. But as the 20th century brought with it an ever-increasing demand for hydrocarbons, researchers from all around the world were working to find more reliable means of accessing them, including a young man named John Clarence Karcher. Karcher was born in Indiana in 1894. His family moved to Oklahoma when he was a child. He studied physics and electrical engineering at the University of Oklahoma and was working on his PhD in Pennsylvania when the United States Bureau of Standards recruited him to help the military during the First World War.
During World War I, scientists were locating artillery shells and bombs by triangulation. They knew that that energy was traveling through the earth, and they were recording it at some distant location. And if you have 3 points around that explosion, you can locate where that explosion is.
Karcher was one of the people involved in this effort, and he learnt a great deal in the process. Once the war was over and he'd completed his doctorate, he returned to work at the University of Oklahoma, where he had already established good relations with many supportive colleagues, including geologists who were experts on what lies beneath the Earth's crust. It was an exciting time. Karcher believed that just as acoustic waves, which move through the air, helped to pinpoint war activity, seismic waves, which move through the Earth, could be used to locate subsurface matter.
He was a young guy. Young kids sometimes have fabulous ideas. And he got this idea that you could use an energy source like an explosion and record the echoes at a surface location and map the subsurface of the Earth.
With a team of colleagues, Karcher's first experiment took place on June the 4th of 1921. A monument marking the event stands behind OKC's Belle Isle Library. This was the first stop of our field trip, which was led by structural geologist Molly Turco.
Well, welcome everybody. I hope you're enjoying this monument. Part of our deep geophysical history. Jan, I don't know do you want to talk about this one?
Yes, his notes say the first location was 1.5 miles west of the Belle Isle amusement park. So that's as close to the location as we know. So the monument was placed here in 1971 when they celebrated the 50th anniversary. They've got lots of rock samples around the base of the top piece of the monument, and all of those rock samples represent oil and gas producing formations in the area.
In the field trip guide, Molly Turco had listed some talking points for each site we visited.
How is seismic data acquired? Like what do you need to get seismic data?
So there's a source, the waves go down, they hit a contrast and acoustic impedance, which is velocity and density. They come back, they're recorded someplace else, and then the processing is all the geometric corrections.
This stuff was probably very basic for most people present, but it was new to me. So as we continued on the field trip, I asked Jan to tell me more. For example, what had Karcher used for the source? How had the initial sound been produced? And how was the information it sent captured?
They used a dynamite charge. They had some kind of microphone that was attached into the ground with a spike so that it could feel the ground motion. And the microphones had a mirror attached, and they had a light beaming on the mirror, and the mirror reflected the light onto photographic film that was advancing at a certain rate so that the light would expose the photographic film in the form of wiggles as that microphone wiggled up and down. To my mind, this was an ingenious contraption to record this.
No kidding. My head was spinning. So the Belle Isle experiment was promising. From the photographic films, it was clear that the method was showing different layers of subsurface rocks. This is because the rate at which sound travels through matter varies according to the type of matter. But since the Karcher team didn't know exactly what rock layers were beneath Belle Isle, nor how thick they were, they had to organise a new experiment. For this, Karcher needed to find a location with a variety of subsurface rocks in uneven formations and which had already been measured and documented. He decided to look for a site within the Arbuckle Mountains, where he knew that there were many irregular rock layers which geologists had carefully mapped out. In fact, there are lots of places where drastically distorted rock layers are exposed at surface level via outcrops. We looked at a number of them during the field trip. Then the final stop took us very close to where that second and all-important experiment had taken place.
How did we know how to find the original location? That was kind of a mystery at some point in time. The way we found the location was through his publications, the way he described it. So he described it as a long Vines Branch Creek, which flowed along the base of an eastward plunging dome capped by the Viola.
Molly pointed towards the direction where the experiment had taken place, though the actual site was hidden from our view by a ridge. Karcher had chosen an area beneath which geologists had already mapped out where and how the layers of the Sylvan Shale and Viola limestone were formed, also their changing thicknesses and where they actually met. Though both rock layers dipped at angles, they did so at different rates. When the results of the second experiment turned out to match up precisely with the pre-existing maps and measurements of the area, Karcher knew that his theory had worked. It was a scientific triumph.
By proving this concept, he was then able to map subsurface structures that were not evident from the surface of the Earth.
Ironically, Karcher's breakthrough took place at a time when oil prices were very low, so it took a few years before his work began to reap economic benefits. In 1928, the first productive oil wells were drilled using reflection seismology. Countless others followed. In addition to being a scientist, Karcher also became a successful businessman. He died in 1978. Meanwhile, the seismic reflection methodology he invented has evolved exponentially. It still provides the basic means of locating oil and gas and has developed in many other directions. This was evident in some of the research that was presented in poster format back at the OKC meeting. Silas Adeolawa Samuel is a PhD student at Oklahoma State. His work uses reflection seismology for environmental purposes.
We need to find ways to reduce the effects of climate change. So one of the ways my research is trying to fix that would be by finding storage sites in the underground where you could store captured CO2 from the atmosphere. So what my research does is we try to find sites where you have a lot of space as well as are safe.
The sieve is needed so that the CO2 can move downwards. Bobby Buist is studying for his PhD at OU. He's using seismic data to explore the ancient history of a buried valley in the southwestern part of Oklahoma.
It is commonly agreed that there's glaciers and glaciation at the poles of the Earth. However, if this valley, which was at a higher elevation, was made by a glacier, then that's sort of counterintuitive to what people know as of right now. So if it's made by a glacier, it sort of reshapes our understanding of Earth's history.
In other words, the work conducted by Karcher and his team in Oklahoma back in 1921 remains extraordinarily relevant today.
This technology is used for environmental work. They use related technology for archaeological work, Native American burial grounds. They're using it in Tulsa, Oklahoma to find mass graves from the race massacre up there. Ultrasounds that we routinely do for medical tests, that is the exact same technology that Karcher developed. It has widespread use to all kinds of modern life.
That's geophysicist Jan Dodson. And I'm so grateful to Jan for bringing such an important Oklahoma story to the attention of How Curious. And you can see photos from the field trip on the How Curious webpage. Just search for How Curious and KGOU. How Curious is a production of KGOU Public Radio. It's produced by me, Rachel Hopkin. The editor is Logan Layden, and David Gray composed our theme music. I'd like to say special thanks to Professors James Knapp and Brett Carpenter, as well as to the many other participants of the Seismic Reflection Centennial. Thanks also to Daniel Turek and Nick Wines. And remember, if you have an Oklahoma-related question or idea for How Curious, email us at curious@kgou.org.
From an Iraq War cover-up to towns ravaged by opioids, to the roots of our modern immigration crisis, Embedded explores what's been sealed off and undisclosed. NPR's original investigative podcast reveals why these stories and the people behind them matter. Listen to the Embedded podcast, only from NPR.